I'd like to do now is a little more in-depth look at the role of nutrients and the management of nutrients and the role of salinity and the management of salinity on Great Salt Lake. Some of you may remember last year during the SEG-aligned Artemia workshop that was held in Shanghai in September. I had a few final slides. One of them was this slide, where I tried to put together all of the different stakeholders that were involved in the Great Salt Lake ecosystem research. Today, I've talked a little bit more about the Great Salt Lake Ecosystem Project under the Division of Wildlife Resources. Tim has given us an overview of the Great Salt Lake Advisory Council and what their role has been. What I'd like to do now is look at the management of salinity and the management of nutrients and how that came about and what we're doing with regard to those two main drivers of the Artemia population. For sure, salinity is an important driver of Artemia. We know that. If we take a look at salinity, there are some thresholds where we get into trouble with the Artemia population. At lower salinity, we tend to get some predation of here on the Great Salt Lake, primarily corixids. That starts to happen at a salinity of around 100 ppt, and then it increases significantly by the time the lake reaches somewhere close to 60, 50 ppt. The Artemia population is totally decimated. What we've also seen on Great Salt Lake, interestingly, is that at these lower salinity ranges between 80 and 100 ppt, we see some phytoplankton assemblages that are negatively affecting the Artemia population. Primarily, we've seen pinnate diatoms here that tend to be really large planktonic organisms that are difficult for the early life stages of Artemia to ingest. So if you look at these findings at the lower salinity ranges, a safe level is, or a safe threshold is probably somewhere above 100 ppt. On the other hand, you also see that at the higher salinities, you start to see population level effects as a result of reductions in survival, in maturation, and reproduction. There's many authors that have published these kind of studies. We've seen ourselves on Great Salt Lake that with the Artemia franciscana that we have here, that starts to happen around 180 ppt, where we start to see significant reductions in survival. So again, these findings indicate that the thresholds where we could talk about somewhat of a safe zone for Artemia is somewhere between 100 and 180 ppt. Now, on the Great Salt Lake, we also have a lot of variability in lake levels within a year as a result of spring inflows and summer evaporation. And those changes in lake level result in changes in salinity of approximately, can be around 20 ppt per within a year. And so if you add that salinity, those salinity variations that happen within a year, then you would want to tighten up that safe range a little bit and look at maybe 120 to 160 ppt as the salinity levels to where you want to start taking some actions. So then the question becomes, well, what can you do if the salinity goes up? What can you do about it? On the Great Salt Lake, we have a causeway that bisects the lake, and it was built in 1959 or finished in 1959. And as a result, and that causeway divides the lake in a north and a south part. And interestingly, all of the rivers, all of the main inflows come in to the southern part of the Great Salt Lake. As a result of that, we see significant salinity differences between more or less saturated north arm of the lake and less dense brine in the south arm of the lake as a result of that inflow of fresh water that's happening at the south part. Now, originally, there were two culverts, two openings in that causeway, in that dam, if you want, and that allowed for flow of water between the north and the south part of the lake. These culverts failed in the probably about 11, 12 years ago. They were significantly failing. And as a result of that, a breach was established. A breach was put into place in 2016 to reestablish that flow between the north and the south arm of the lake. Now, when that breach was put in place, or even before it was put in place, the Great Salt Lake Advisory Council really saw an opportunity there and recommended to the state that they design this breach with an adaptive management berm, that would help us manage salinity in the south arm. So taking a look at that adaptive management berm, if you look at the breach, and you would take a cross section of the breach, then that cross section would look a little bit like this schematic diagram, where on the right, or on the south side, you find lower density brine. On the north, and with that lower density brine, you have the riverine inflows on the south. Those inflows then push some of the water towards the north. And also those inflows of fresh water have a tendency to decrease the salinity in the south. On the flip side, on the north, you have really heavy brine, high salinity, near saturation or at saturation. And because of that high salinity, the pressure at the bottom of the lake, at the lower or at the higher depths, becomes actually becomes higher. And as a result of that, you get a return flow of that heavy brine that flows back under the low salinity brine, flows back to the south arm, and that tends to increase the salinity. Now, with this adaptive management berm in place, if you would increase the size of that adaptive management berm, you would be able to block that return flow of heavy brine. And as a result of that, you can again decrease the salinity in the south arm of the lake. That's the schematics, that's the principles. The principles seem rather simple. The execution of that is actually a little bit more difficult. But let's look at the process. The Great Salt Lake Advisory Council, as mentioned before, recommended an adaptive salinity management. The two state agencies that have responsibility here are the Division of Water Quality. They're responsible for the water. And then you have the Division of Forestry, Fire, and State Lands, and they're responsible for the land under the water. So together, these two agencies created the Great Salt Lake Salinity Advisory Committee. That advisory committee is made up of multiple stakeholders. And, those stakeholders include government agencies, they include research institutes, they include industry, and together these stakeholders have one goal, and that is to develop and provide recommendations to the Division of Forestry, Fire, and State Lands and the Division of Water Quality on the long-term management of the salinity of Great Salt Lake. What has that advisory committee done so far? The first things that we did was about 3 years ago is we started an intercalibration exercise, because the different researchers were using different ways of evaluating salinity by density, by conductivity, with refractometers. And so we needed to sort of standardize ways to evaluate salinity. The next thing that we did as an advisory committee is come up with an ideal salinity range for all of the different biota in the Great Salt Lake, and also for an optimal salinity range for the different industries that use the Great Salt Lake. And you can sort of see here in the top right hand corner of the slide, you see some yellow and orange zones, and you see at least one zone in there that's either all green or yellow. Green meaning optimal, yellow meaning acceptable for the biota of Great Salt Lake. And so that zone is what the advisory committee targeted on. And as a result of that, the committee advised the state agencies to maintain the salinity of the south arm of Great Salt Lake within 120 to 160 ppt to be the target salinity for the south arm of the Great Salt Lake. What's that committee doing now? That committee is now developing the salinity models in order to be able to advise the state agencies on how exactly to maintain that salinity within that range. Who are the groups that are working on these models? We have the USGS, United States Geological Survey, that's doing flow and salinity modeling. The Utah State University that is doing the more complex CFD modeling of the breach itself, of the opening between the north and the south itself. And then our own cooperative that is modeling all of our historic salinity data to come up with some conclusions as to how we may help with the management of the salinity in the south arm of the lake. Some interesting observations that we made looking at historic salinity levels, values, is that prior to the failing of these openings, these culverts in that dike, the south part of the Great Salt Lake had an upper brine layer, an epilimnium, shown here at the bottom left-hand side in blue, and a deeper brine layer that was made up of heavier brine, ammonium at the bottom of the lake. What we saw happen, and go back one here, this state of the Great Salt Lake is shown in the right-hand graph with the little black dots. And what you can see here is that you have a certain relationship between the elevation of the lake and the salinity of the lake with these culverts or these openings in place. What we saw when these openings started to fail is the demise of that deep brine layer. That deep brine layer disappeared, and we started to see a different relationship between the salinity and the elevation of Great Salt Lake, shown here by the orange dots. And then when the breach was constructed, the new breach was constructed to replace the failing culverts, we started to see that deep brine layer come back. And we started to see here, shown with the little white and red dots, we started to see that relationship slowly return to what it was prior. The reason why this historic information was important to us is that it gave us a sense that, yes, indeed, by managing the return flow of that heavy brine from north to south, we can either help increase the salinity in the south, or we can help to decrease that salinity in the south. What we did then is we took all that salinity data, we integrated the salinity at different depths with the bathymetry of the lake. And so we were able to not just then look at salinity, but look at the actual salt mass that was available in the south arm in both the deep brine layer and in the upper brine layer, because we were able to identify where that chemocline was as a result of our sampling efforts throughout the years. We then evaluated that salt mass, here shown on the right, for both the deep brine layer and the upper brine layer, and we could integrate those and look at the total salt mass. And then you can see again the evolution of the salt mass that happens when that new breach was put in place, and how it's at first you see a loss of salt because of the head difference, and then you start to see that salt increase as a result of the return of the deep brine layer. So with that information, everybody was on board that indeed that adaptive management berm could be used to either increase the salinity, or if the berm is increased in height and blocking the return flow of heavy brine, decrease the salinity. Now, all of this looks really simple, but at the end of the day, we need to figure out what kind of architecture that adaptive management berm needs to be constructed around in order to obtain those target salinities. And that's where Utah State is coming in. The Great Salt Lake Advisory Council first commissioned a computational fluid dynamic model of that breach. These are pretty complex models where these modelers use supercomputers that they run iterations on during several weeks to really refine their models to get a better look at the hydrology of what is happening in these sort of complex interchanges between the north and the south arm with the different salinities in both of these places. And there was a recent publication with regard to that, and more work is being done. But at this point in time, what the researchers are doing is really just refining that modeling in order to determine the optimal berm architecture. And as a result of that refinement, the Department of Forestry, Fire, and State Lands is already engineering the requirements for the adjustments of that adaptive management berm. So in conclusion, we have some unique natural and some unique man-made features on the Great Salt Lake that are really the basis for the salinity management. The recently constructed adaptive management berm allows for us to actively manage the salinity in the south arm of the lake. Recommendations are now in place to manage that salinity within a range of 120 to 160 ppt, and the state is in the last phase of the modeling and the engineering of the adaptive berm in order to implement the management of salinity per our recent recommendations. So again, what you see here is a collaborative process that results in a successful salinity management tool developed for the south arm of the Great Salt Lake, again, helping, in our case, helping sustain the Artemia levels in an optimal range, but also supporting all of the lake biota. Another important driver of the Great Salt Lake ecosystem are the nutrients. And again, we have here the Great Salt Lake Ecosystem Project with the Division of Wildlife Resources that is coordinating, I would say, a lot of that nutrient work. We have overarching this work, the Utah Division of Water Quality, that's truly responsible for criteria development of the aquatic systems. We have the USGS that's studying nutrient inflows and nutrient cycling, the Brine Shrimp Cooperative, who is looking at nutrients in the pelagic zone and nutrient enrichment, University of Notre Dame, who is looking primarily at modeling of the whole ecosystem. So what are the nutrient studies that are being done? Let me first talk about the USGS. They've been working on inflow data for a couple of decades now, primarily looking at nitrogen and phosphorus. And overall, if you look at all of their data, you can see that the inflows of nitrogen especially represent less than 10% of the total nutrients that are coming in or that are part of that south arm of the Great Salt Lake at any one time. That's important. It's important for two reasons. It tells us that, one, yes, most of the nutrients are really being cycled within the different trophic levels of the Great Salt Lake ecosystem, but somewhere between 5 and 10% of nutrient inflow is important to maintain adequate nutrient levels in the long term. More recently, the USGS has been focused on nutrient cycling. There's a lot that we still don't know about the nutrient cycling in the Great Salt Lake. So they're looking at the benthos, the deep brine layer, the epilymnium, the different trophic levels, atmospheric deposition and volatilization, nutrient sequestration, and so on, so that we can get a better overall picture of what's going on with nutrients in Great Salt Lake. What have we been doing at our cooperative? We've looked at some nutrient cycling, especially between ammonia and the Artemia population. We do see some ammonia peaks on the Great Salt Lake. There was some concern by the Division of Water Quality as a result of those peaks. We were able to demonstrate, and that was accepted by the division, that these peaks are really the result of a dying or first a growth and then later a die-off of the Artemia population, and that they were part of the natural cycling within our hypersaline system. What we also were able to demonstrate is that the lake is still significantly nutrient limited, primarily nitrogen, but also co-limited nitrogen and phosphorus. We're not the only groups that have researched that, but what that really indicates is that the lake still has a high capacity for additional nutrient absorption, or alternatively, if the volume of the lake is to decrease further, then those nutrients would just concentrate and still be available to the biota of the lake. And by way of example, I would say that between 2012 and 2016, the industry harvested an average of about 1,400 metric tons of dry Artemia cysts of the Great Salt Lake. The next 5 years, between 2017 and 21, the average harvest of the industry was about 30% higher, while the lake volume was reduced by 20%. So this is really indicative that the lake volume is not the primary driver here of the Artemia population, but that it is the nutrients that are the primary drivers here. So that brings in the Division of Water Quality. Division of Water Quality is responsible for the development of nutrient criteria, more specific numeric nutrient criteria. They're under obligation to do that by the Environmental Protection Agency of the United States. And so the division created a nutrient core advisory team and a nutrient technical review team that was responsible to advise the division on how to create these numeric nutrient criteria. And again, these advisory teams and this technical team was made up of multiple stakeholders and multiple experts from the different stakeholders. And because of that involvement of these different stakeholders and because of that expertise, and because of the willingness of the Division of Water Quality, understanding the research that had already been done, they were willing to create some very unique nutrient criteria. It was the first time that it was done in the United States, and it was done based on ecological responses. So they are numeric criteria, but they're based on ecological responses. And as a result of that, the division was able to create criteria that protects beneficial uses of our Utah streams while still considering the needs of the other aquatic ecosystems in Utah, including the Great Salt Lake. And an example of the willingness of the division to work with the different stakeholders, I just want to give it by way of an example here, but a really unique, again, approach to nutrient management is, with all this research in place, understanding the importance of nutrient flow into the south arm of the Great Salt Lake. The division was looking at a problem that was created. If you look at the map here shown by this little white arrow, there was a public water treatment that was bringing in treated water into a brackish area of the lake called Farmington Bay, an area that is bisected by a small causeway from the rest of the south arm of the Great Salt Lake. And that influx of that nutrient-rich water created some unfavorable algal blooms in Farmington Bay. What the division then suggested, understanding the need for these nutrients, it suggested to just move the outflow of those treatment works towards the north part of that dam so that those nutrients could go directly into the Gilbert Bay, into the area of the Great Salt Lake that supports the Artemia population. It did require, and this is in process, but it's requiring a 6-mile pipeline to be built for this to be achieved. But it is just an example of some of these unique solutions that we come up with in order to try and maintain the ecology of the Great Salt Lake. So what can we conclude about nutrients here? We've got nutrient cycling that is really important. We know that, and there are significant efforts on their way now to further study that cycling. We know the lake is nutrient limited. We know it can maintain a significant Artemia population even at a decreased volume. We know that, yes, primarily there's nutrient cycling ongoing, but there is an importance of replenishing those nutrients. And we have state authorities that now recognize that need to maintain that nutrient inflow into the Great Salt Lake, and they're making some real efforts to help that happen. So nutrient management and nutrient limitations at the end of the day protect our Great Salt Lake against further receding lake levels. So in general conclusions for me, we've got 25 years of collaborative management and research. It's resulted in the implementation of a successful sustainable harvest management, some unique tools to maintain the salinity at optimal levels, and some nutrient management that supports a healthy brine shrimp population regardless of lake levels. And as a result of all that work, we feel we have really a very resilient ecosystem today that's able to produce stable populations of Artemia and is projected to do so at least for the foreseeable future. And with that, I thank you for listening.